Hello, my name is Jeff Rockauer, and this is my presentation on Green Lights Forever, analyzing the security of traffic infrastructure. It truly is a dream of every driver that's ever been stuck in traffic to get a green light at every time you approach the intersection. As you may not recognize this paper from the list that Dr. Wang has provided, I have had prior approval to use this paper, and I chose it as it relates to my daily job functions. Anatomy of a traffic intersection. Sensors are a key part of the traffic intersection. Induction loops are a tried-true method where type BL wire, which stands for brass linguini, is embedded in the roadway as shown in the middle picture and acts as an induction loop, and the magnetic field is changed anytime a piece of metal changes over top of it. Another sensor type would be a video image detector, also called VIDS. What is depicted on the left shows two boxes which mimic the induction loops shown on the previous slide. Should a vehicle enter those boxes, then it will act as an induction loop, sending a call signal to the controller. As shown on the right from an autoscope image, there is not only that induction loop, but also the stop bar present, as shown with the blue arrow. Once a vehicle passes a stop bar, other things happen in the controller which can advance a signal cycle. There are a couple other sensors that I'd like to mention, which include radar, infrared, and magnetometers. A traffic signal controller is the brain of the intersection. It decides when there is a green light, a red light, a yellow light, and when it should send timings in a certain pattern. Communications of the traffic intersection studied is from controller to controller, controller to sensors, and it communicated wirelessly in this study. A malfunction management unit is also called a conflict monitor. It's the last resource of protection against failed traffic signals and misconfigurations, such as green at all approaches. Case study. This case study studied a centralized system rather than a decentralized system. So everything reports back to a central server. The server makes modifications to light timings at specific intersections. The authors believe that even if the intersections use different radios or even wired connections between the intersections, they have no reason to believe that any fundamental differences exist between the network studied and other traffic signal systems. Many traffic infrastructure devices created by various vendors and installed by various transportation departments will have similar security properties due to lack of security conscientiousness in the entire field. As depicted in the Venn diagram on the right, security, cybersecurity specifically, is one concern in IT. Transportation engineering is another concern in the civil engineering world. Overlapping them creates hopefully a secure infrastructure. Within the road agency's network, intersections are connected in a tree topology with information flowing to a root node. The root node communicates with the central management server, which can send commands to any intersection on the network. There are wireless connections for the intersections that use commercially available ISM bands. They are unlicensed frequencies. Both frequencies use radios with unencrypted traffic and use default usernames and passwords. The 5.8 gigahertz band, preferred due to higher data rates, uses a proprietary point-to-point or point-to-multipoint connection similar to 802.11. The SSID is broadcasted and completely visible to laptops and smartphones, but they can't connect. Configuration software is available that allows customized credentials, but it must be the same across the entire network. 900 MHz frequency is used when there is no direct line of sight and the connection is typically going through obstructions such as buildings or terrain. These radios use a proprietary version of frequency hopping spread spectrum via point-to-point connections. Both sides of the connection must know the network name and a 16-bit slave ID value. There are similar software issues, but by customizing the credentials, the software no longer works since it assumes the default username and password. The switches used in the cabinets are commercially available and unfortunately don't use any security features. Also, they have default credentials. The controller reads sensor data and controls traffic lights. Many settings are programmable, which allows fine-tuning of the intersection via an onboard logic processor. Basic if-then-else logic is used for the operation. An example logic statement shown prevents traffic-controlled lights from changing state. The controller is given a Boolean statement and corresponding actions. Selecting the same action in both cases forces the controller to enter a chosen state regardless of the condition. In the example shown, the controller is set to stop time, a state where the lights are frozen in the current state. All of the settings on the controller can be changed through the physical interface, just as well as through the network interface. The FTP connections are available to the device and allow access to a writable configuration database. It requires credentials to access the interface. The username and password are unfortunately hard-coded values which can't be changed and are freely available online. The controller used in the study conforms to NTCP 1202, which specifies communication standards for traffic signal systems. The protocol allows commands to be sent to and from the controller. NTCP stands for National Transportation Communications for ITS protocol. The controller runs VxWorks 5.5 real-time operating system. It's also used by NASA and probes and satellites, but this specific version of VxWorks, version 5.5, the default build leaves a debug port open for testing, but it should be closed for production cases. It's very easily closed in a minor change to the OS, but is normally forgotten about too often. ICS-CERT issued a warning about this. Connecting to the port requires no password and allows for reading and writing of device memory. Even though the study focused on attacking the network and controller, other devices can be targeted too. Cameras at the intersections record color video and unfortunately allow PTZ, which is pan, tilt, and zoom. And should an adversary change the position of the camera, then the video analytics could be thrown off and forced to detect movement at an incorrect location. In addition, spoofed sensor data can be used to manipulate traffic light states. 3 major weaknesses were found. The network is accessible due to the lack of encryption of data. The devices in the network lack secure authentication due to the use of default usernames and passwords. And the traffic controller is vulnerable to known exploits. Attacks. Displayed on the right is the intersection used for field tests. The targeted infrastructure controls a T intersection. The fail-safe state of the intersection is a blinking yellow light on the main road and a blinking red light on the side road. At the left of the picture is the traffic controller cabinet, which contains the controller, the switch, and the MMU. Radios and the video cameras are located on top of the pole or on the traffic arms. The threat model assumes the attacker infiltrates through the wireless infrastructure and has sufficient resources and motivation to monitor the network for extended periods of time. Also assume funds are available to purchase identical radio equipment. Make and models of the radios are typically stamped on the devices themselves. Assume there is no physical access to the traffic infrastructure. Should that be the case, the attacker could remove all fail-safe equipment, such as removing the MMU or the conflict monitor, which prevents green in all directions. Attacking the network would be possible first by accessing the network. Once gaining access, then attack devices in the traffic signal system. The process varies between radio types and configurations. Once the network is accessed at any single point, the attacker can send commands to any intersections on the network. A hacker only needs access to the weakest link in order to get in. The 5.8 GHz radios made no attempt to conceal or encrypt their network traffic. Anyone with a wireless card capable of 5.8 GHz can easily identify the SSID, since the SSID broadcasting was not turned off. Since this is a proprietary protocol used with the radios, it won't be possible to connect through standard Wi-Fi. These radios are not typically available to the public, but the researchers social engineered the way out of this. And again, since there is no encryption, the researchers successfully connected to the wireless network. They were able to connect to the radios from over a half a mile away from the radio in question. The 900 MHz radios proved to be a little different. Attacking them requires knowing the network name and a 16-bit slave ID value. Sniffing for the network name proved to be challenging due to the proprietary protocol used in the frequency hopping spread spectrum. With appropriate hardware, it is solvable to fix in on the frequency hopper spread spectrum. In addition, there has been previous work showing that frequency hopping is not inherently secure. Although the proprietary protocol could be reverse engineered, it is easily overcome by purchasing compatible hardware. The 16-bit ID value was overcome by brute forcing the radios to determine the correct ID. A complete brute force of all 65,536 values could take up to several days, but the integrators typically choose lower number values. This attack was successful after only a couple minutes. Once on the network, there are two primary methods for accessing the controller. The operating system's debug port is open by default. It gives the attacker the ability to read and write arbitrary memory locations, kill tasks, reboot the device, and whatever else he has in mind. It can be used in a sophisticated way to reprogram the controller as desired. The authors created a program via this vulnerability to dump the online memory contents from the controller as proof of concept. The remote control capabilities built into the controller itself by NTC-IP 1202 allowed yet another method of accessing the controller via the network. NTC-IP isn't a secure protocol in today's standards. There are articles online to reverse engineer the protocol, since it has a vulnerable version of SNMP, which is version 1. The attacker can craft a UDP packet which mimics a key pressed in the front of the controller. The controller vendor leased a program to operators to remotely configure a controller through this protocol. The authors sniffed the packets between the controller and the program. All of the packets were unencrypted and in clear text, requiring no authentication and is easily repeatable. The authors were able to partially reverse engineer the protocol. They created a program that allows a user to activate any button on the controller and then displays the results to the user. Afterwards, they created a library of commands which allowed scriptable attacks. The controllers were fully accessible through this makeshift program they have created. After gaining access to the controller, there are many methods available to attack the device. The researchers focus on attacks made possible by accessing the controller through the remote control functionality. Malicious logic statements can be sent to the controller. Possible commands include switching the state of a specific light or freezing the state of an entire intersection. An attacker could choose to advance the lights at a much faster or slower pace than normally desired. Program statements remain present in the controller until it is removed by the operators. Modifying the light timings can be done by changing the timing values of the light states. You can change the minimum and maximum times for each light state, which can be used to shorten or lengthen the timings of specific light states, either to cause congestion or diminish safety. These attacks are possible, but the conflict monitor maintains safety by disallowing many attacks. Conflicting green or yellow lights, or too short of a duration of yellow or red lights. Should this happen, the MMU is activated and sets the intersection to a known safe configuration instead. Other types of attacks are still possible, such as red in all directions or short green times. The aforementioned methods allow an attacker to gain access to the network and controller. Possible attack scenarios and damages dealt are shown, but are in no way an exhaustive list. A denial of service attack includes stopping normal light functionality and loss of service to set all lights to red. It causes traffic gridlock and confusion for drivers. Attacking the MMU by attempting an unsafe configuration can be done remotely, but must be reset in the field by a technician with physical access. An attacker can disable traffic lights faster than technicians can be sent to repair them. It causes safe timings, but in a suboptimal state, and traffic operation centers can notice these, but would be left with the recourse of disabling the network connections between the intersections. Traffic congestion is another type of an attack. More subtly, attacks can be made against the entire traffic infrastructure, which can manipulate the timings of an intersection relative to its neighbors. The effect would be a poorly managed road network, which causes significant traffic congestion. This is far less detectable than other attacks. A study in the city of Boston calculated that reconfiguring the timings of 60 intersections could save $1.2 million per year in person hours, safety, emissions, and energy costs. This study focused on about 100 intersections. Light control can be done for personal gain or for criminal advantages. Lights can be changed to be green along the route the attacker is driving, such as Hollywood movies depict. This could easily be assisted by triggering a preemption signal call to allow green to only that approach. Typically, this is used by emergency vehicles. Light could also be changed to all red coordination with another attack, with the purpose of causing traffic congestion and or gridlock with likely motor vehicle accidents. This would obviously slow the response of emergency vehicles. Recommendations. Recommendations on the wireless security include disabling the SSID broadcasting, and on the 5.8 GHz radios to use WPA2 encryption. The 900 MHz radios only support WEP or WPA, which should have been turned on regardless. Enabling encryption on the wireless radios requires establishing a set of encryption keys. These should be unique across each master and slave radio pair. Even a single key used across the network would make it far more secure than the current setup. Firewalls are also recommended. If an attacker gains access to the network physically or remotely, many vulnerabilities are still left open. The authors recommend reconfiguring the radios and switches to put restrictions on network traffic whenever possible. Only necessary communication should be allowed through, and unused ports should be blocked entirely, preventing attacks such as accessing the debugger functionality on the controller. Too often, firmware is not kept up to date. Embedded devices should be kept up to date, especially since field-deployed devices makes it a challenge to access. Traffic signal controllers require a police setup and turning off the signal in the middle of the night. Updating the radio and traffic controller firmware is a must. The controller examined had outdated firmware and missing critical security updates that protected them against the VxWorks debug port issue. The vendor's update logs didn't even mention the debug port to the public. Transparency on part of the vendor could encourage the customers to update sooner. Another recommendation was changing the default credentials. Every single device studied in the deployment used default credentials that came built into the devices. Default credentials are easily found on the internet and provide no security at all. Hackers who have gained control of the network and devices can easily change the default credentials and locking out the owners and operators of these devices. Change all credentials in a lab before deployment in the field. Encourage the device manufacturers to not hard code usernames and passwords. This is especially true for the FTP credentials of the controller. Broader lessons. The findings carry lessons beyond their immediate implications for traffic infrastructure. This section has a broad view and considers how the study can teach us about embedded security systems. Network trust. It is not enough to trust the network that will be secure or physically isolated. The CAN bus and cars are considered trusted, but attackers can penetrate them with physical access or by remotely exploiting the various vehicle subsystems. SCADA systems, supervisory control and data acquisition, normally talk on unencrypted protocols, but many systems have been found attached to the public internet. The attackers gained full control of devices over a wide deployment by compromising a point of the poorly secured wireless network. The trusted network assumption fails when even a single vulnerability or misconfiguration exists anywhere on the network. A safer approach assumes the network is open and possibly connected to the public internet. Devices should apply end-to-end encryption and authentication by using Secure Shell or TLS. Key management should allow an individual device to fail without compromising the rest of the network. There is also a complete lack of layered security in embedded systems that have been learned. The deployment studied obviously was vulnerable to attacks, but could have been much worse without the protection by the MMU. Signal systems use MMU as a safety feature to make sure lights enter a so-called safe mode should the controller have a fault. This ability requires reliability to detect if the controller is operating in an unsafe state, and it can override the controller to force it into that fail-safe mode. Other embedded systems should consider similar dedicated fail-safe hardware. MMUs were designed as a safety feature. The security it provides is as a result of conservative engineering. Fail-safe hardware should be isolated from software, but unfortunately, there has been discussion of having MMUs being software-based rather than electronic circuits. Remember, safety features do not equal increased security. Historically, traffic control systems follow an unfortunately familiar pattern. First, they're purely electronic devices, then they are computer-controlled devices, and then these computer-controlled devices become networked. Each advance in technology seems like a natural step, but when devices have been computerized and networked, they are being exposed to an array of new security risks. The results for the study suggest that the developers, customers, and regulatory frameworks were caught unprepared. Other embedded systems which became computerized and networked have faced similar security phase changes like automobiles, electronic voting machines, and medical devices. In each case, security was weakened and with catastrophic security failures. Embedded designers should try not to repeat this historical trend and be more proactive in their designs. Related work. Before diving into related work, I just want to mention that this study is the first publicly available security evaluation of a deployed traffic infrastructure system. Other studies are available on adaptive traffic signal systems, but most barely touch on the security. Additional studies are available for both physical and computer-based attacks, but again tend to be generalized, which don't investigate specific computer-based security weaknesses. The city of Austin, Texas, did a security evaluation of its traffic lights, but the results were held confidentially. Other works were able to reverse engineer the databases of a major traffic controller's database, Econoly. Magnetometers by Census, also called pucks, are embedded in the pavement up to 6 inches deep and had their wireless communication reverse engineered since, again, the network traffic was unsecured. Security of critical infrastructure is paramount. Security of automobile systems have been studied extensively, showing various flaws in design and implementation. At a conference in January, I was exposed to what's called the Car Hacker's Handbook. It's freely available online, downloadable, and even purchasable through Amazon. Future work. The traffic signal controllers that were examined return an SNMP banner that uniquely identifies them. Several devices have even been discovered responding to this banner in the internet. Even though the traffic infrastructure may seem complex today, the future awaits the transportation industry with major funding and initiatives by the US DOT and the Federal Highway Administration for superbly more elaborate systems with vehicle-to-vehicle and vehicle-to-infrastructure systems. Although these systems may have safety in mind, it may be forgetting the importance of security. It could allow attackers to inject malicious data or code into V2V or V2I networks. Conclusion. In addition to the recommendations made by the researchers, I also want to suggest that the wireless would be improved. Dedicated frequencies are available for public safety at the 4.9 gigahertz range. There's also licensed wireless frequencies which are registered with FCC. No one else can use them other than the person who is licensed for it. Cellular mobile private networks are available through carriers such as Verizon using private IPs at the device that connect through a secure network over the cellular network, almost like a VPN. I think that the communication should have been hardwired. Although this could be costly at times to bury, it does pay off in the long run. Fiber optics have a lifespan of at least 25 years, and assuming that the mice don't eat them. And copper would be used such as coaxial. The cost and complexity of fiber optics has dramatically decreased with time, as copper has unfortunately increased. I truly feel that the authors of the paper were missing out on suggesting standard operating procedures for revisiting security of traffic infrastructure regularly. They also should be conforming to the NIST cybersecurity framework. following the presidential executive orders 13636, 13691, 13800, etc., is an absolute must for federally funded projects, as the feds can easily take that money away. I just want to leave off with saying that the most secure systems are still vulnerable to people, and sometimes a complex solution is not always the best method.